how are you guys today? And does anyone have any questions? All right. Well, we have been on chapter 4 for about 2 weeks now, and I feel at this point we've got a good baseline for Newton's laws and the various types of force that we're going to be looking at for the rest of the course. So my goal for today is to begin the next chapter, and that will be the last new chapter before the upcoming test. So we're going to start chapter 5, which is a direct continuation from 4. 4 was mostly about force itself. 5 is going to be about how we use energy and force in order to do work and other tasks. And 5 will be the last new piece of information before said upcoming test. I am planning about 1 week, or really 3 lectures worth of chapter 5 stuff. So my plan is to start it today, be wrapping it up by or around the 27th of next week, and then Friday of next week, the 29th, we will move into test review territory, where I summarize the past, I guess, month and a half of learning to make sure everyone is ready for said upcoming test. Again, I point this out a lot, but I just want to make sure everyone has it on their radar. That test will be the week of Monday the 2nd through the 6th October. And again, that test will be during lab time. You won't have a lab that week. You'll show up here instead to take said test. And for every test, I always, ahead of time, want to take time in class to summarize everything and to show the study guide and practice test that I make for every test. Study guide is just going to be the list of all the concepts, chapter 1 through 5, that you should be familiar with. And practice test, I always write it after I write the test so that it's different questions that use the same principles and same techniques.
Would you say that the tests and practice tests are closer to what we do in class than the homework?
Overall, yes. Homework is designed for you to be able to work on it over time with classmates, and also with tutors if you come to the study sessions on Tuesdays and Thursdays. Test is designed for you to be able to come in, do it quickly to the best of your ability, and then go on about your business. So the homework sometimes has some head scratchers, since the idea is you're able to do them in a comfortable environment and come back to them later. Test is designed to be one and done. Nothing's meant to take up a bunch of time. It's just meant to gauge what you know. Does that answer the question? Okay.
Is the exam more of like a combination of definitions and problems?
It is mostly math. The current draft has 9 questions, of which 2 of them are short answer in nature. One of them is, well, I'm not going to give all the game away. I will. Sorry, I'm psyching myself out. One of the questions on test 1 is always identify the laws of motion from these 5 statements. I mentioned that when we looked over the laws. One of my test questions, and also one of my end of course exam questions, is always, here are 5 statements, which 3 are laws of motion, and then number them. So I'm going to go ahead and tell you that's one of them. There's also usually at least one other not math-based question. The rest of them are usually math-based, but I write them in a way that I am trying to look for and understand see what principles that you know. And even if you are looking at something and blanking on the math, I give you points if you start writing paragraphs about the physics you know in relationship to what's going on. So if I ask you a projectile motion question, and you are just drawing a blank, and you just write out a paragraph about gravity and 2-dimensional motion and things like that, that will net you points. So you do have to do math to get an A, but you can still pass without doing math.
Are the questions more like the style in the PowerPoints?
Yes. Yeah, the homework questions are designed for you to do them outside of class in a comfortable environment. Class stuff is meant to be what, yeah, I teach you the stuff in class and then the test questions are more like that. And again, I'm gonna make a practice test, which again was also written by me after I finished the main test. So if you look at the practice test and everything feels good, if you can do those types of questions, you'll be good on the test. And all that practice material will be ready by, like posted to Brightspace by the 29th so we can review everything together in class. And additionally, lecture during test week will also be primarily review focused, like answering questions from you guys. If you're working on like the practice test and the homeworks, I want you to ask about them during lecture during this week. Because again, test isn't in lecture, it's in lab. So lecture is good review time. Additionally, that means if you say attend Monday lab and get the test over with, you can kind of take the rest of the week off if you want to. I would, like officially, class is still meeting and you can come ask questions about like the homework you're working on. But if you've already taken the test, lecture is mostly gonna be test review focused. So attendance is not required once you get the test done for that week. Thank you, I tried. I'll also point out even further that this is test week. Monday and Tuesday after that's fall break, right? I'm not misremembering. So fall break here, which also means no lab at all the following week. So that's another mini vacation. We'll have lecture Wednesday and Friday. One of those 2 days will be the day where I give the test back and we look over my answer key together so everyone feels comfortable with the whole thing. And then on Friday the 13th, midterms go out. I promise that statement was not meant to be ominous. Friday the 13th. And the midterm score for this course is your current average. It's not just the test grade. It's a check-in for how you're currently doing across all categories. Which means if you haven't been doing the homework and quizzes, technically that's factored into the midterm, but midterm's just a check-in. Like if it's low because you haven't been doing the homework and homeworks and quizzes, it'll go up when you do them. I do recommend doing them though. It's also still good practice. So again, we're gonna get towards study material in a week. We're gonna cover some of that together, but in the meantime, I do recommend be working on homeworks and quizzes chapter 1 through 5. Not only is it practice for the test, it raises your midterm grade. Questions? Okay. I feel like I've been monologuing for a bit. And frankly, that's going to continue because the beginning of chapter 5 is filled with more monologues than it is of math. So, sorry for that in advance. Any questions or issues before we switch gears slightly? Okay. Oh, yeah.
You said that the homework isn't necessarily due till the end of the semester, but I don't remember what you said exactly, but last class you said that something about the grades of our homework is put on the midterm or something like that?
Yes, because the midterm grade for this class is your current course average, and your current course average does factor in homeworks and quizzes from chapters 1 through 5.
So we should get that to 100% as soon as we can.
Yes, it's good test practice and it helps your midterm score. Now, if you don't do them, again, I'm not going to force you. If you don't do them or if you don't have them completed, like it'll affect your midterm score, but a low midterm score is not the end of the world, especially if you do good on the test. Because if it's low just because you haven't done the homeworks yet, then obviously that'll be fixed by the end of the semester. So, official statement, I highly recommend doing homeworks and quizzes chapter 1 through 5 prior to midterm scores going out. Disclaimer, if you still don't for any reason, a low midterm score is not the end of the world. For that specific reason.
Because I just have I skip 1 or 2 of the questions on the homework.
Yeah, for context, Homework is 10% of the course grade, and there's 10 homework assignments. So each single assignment is like 1% of your grade. And that means each single question on it is like 0.1% of your grade. So they're only part of the grade to get you to do them, if I'm being honest. So like missing a few questions wouldn't change your grade at all, if I'm being honest. And even if you just got 70s on all of them, you know, that's like 3 points off of your total average. I say that out loud. I still get tons of people trying to get 100s on all of them, which is valid. I just say it as a comfort. You don't have to get them flawlessly. Once I get the practice test up, I would definitely say that's the main thing to focus on short term, because the test is a way bigger part of your midterm grade.
Do we get the answers to the practice test?
Yes, I post an answer key for it, and once I grade the tests, I will give them back. They are yours to keep because they will be good study material for the final exam. You keep it. I will show my answer key for it, but I won't post it on Brightspace like I do the practice test answer key. I will also point out, because I don't think I've mentioned this yet, not only do I give partial credit for literally everything on the test, there's bonus points built in. Rather than have one bonus question, I don't like that, because then if you don't know that one thing, you don't get the benefit. I just give you more points than you need to get a 100. So the bonus is built in. You don't have to know the one specific bonus question. I find that covers the most bases. So you can get things wrong and still get over 100. And again, don't leave anything blank, because you earn points for literally anything. I've had people leave frowny faces because they are just stumped, and I give them like 1 out of 10 for it, because it's an answer, it's just not a good one. Any other questions before I start monologuing about something different? All right, so chapter 5 is about 3 primary things: work, energy, and power. And they're all going to tie into what we've done the past week or so, because they're all going to involve force. First couple things we need to talk about are some definitions, the physics definitions of work and energy. Because those are both words that get used a lot in common English, and the physics definitions vary slightly to their common use. In physics, the definition of work is the use and transfer of energy. Alternatively, it is the transformation of energy. It is the act of acting, and in that action, using, transferring, and transforming energy. This means that every single thing you do, you will exert force, and as a result of that, you do work, you use up your own energy reserves. Every single action you take takes energy, correct? And that is why if you do too many actions, you tire yourself out and need a nap and a snack. So, that's our definition of work we're going to be operating from, and given that this is physics, we have a formula to go along with it. Work equals force times displacement. Work is a new variable. I'm going to describe everything you need to know about it. But to quickly summarize the formula as a whole, you do work when you exert force on things and push them some distance. And really that does summarize about every action you take on some level, conscious or subconscious, because every single thing an organic creature does involves forces and motion. Both literally, macro scale in terms of moving your limbs around, but blinking and your heart beating is still force and motion. You just don't control it super consciously. And even like your nerves working involves exerting force on various chemicals and pushing them around. So everything, conscious or subconscious, involves force and motion, and as a result, every action uses energy and does work. So, all forces, as long as they successfully push something a distance, accomplishes some amount of positive work. And we're defining that again as the use, transfer, or transformation of energy. So as long as you're doing one of those things, you are accomplishing work. This means you can use the definition of work to your advantage, because if, say, a parent or guardian asks you, or even a supervisor at your job, asks if you've done your work today, you can pick up any stray object and then honestly say yes. Force and distance, that's all it takes. Now, in this class, work is going to be measured in the unit joules, because that is the metric unit for energy that this course likes. Joules is one of the 2 metric units for energy, actually. Depending on which floor of this building or the adjacent one you live on, you may be more used to using calories, and that's fine and all. Calories is used, I feel, more often for heat and chemical reactions. We're going to stick with joules though, because most of physics' formulas are designed to give you joules. 1 joule of work is the energy required to exert 1 Newton of force over a 1 meter distance. But they do relate directly to each other. 1 joule is about 1/4 of a calorie. Note though, that's heat calories, not food calories. Questions before I move on? Okay. Now, this definition uses the word energy, and so for thoroughness sake, I want to give you the physics definition of energy to go along with it. And the problem with defining energy is that's hard, because we can't really detect energy directly, and we still don't really know what it is. Anytime that you've thought you have observed energy, you've only really observed what matter has done when it possesses energy. Energy is just this weird invisible thing that matter can have that lets it do stuff. And you only really see the doing stuff. You don't see the energy itself. Anytime you think you see it, or when a cartoon author thinks they can see it, what you're seeing is something that matter did because it possessed energy. The best definition for energy I can give, it is something that matter possesses that allows matter to do things. And the best way we can identify energy is by witnessing the things that matter does with it. Off the top of your heads, what are some forms of energy you can think of, or alternatively some things that matter does with energy that you have seen before with your human senses?
Light bulb turn on.
All right, I'm going to call that light. I'm also going to list electricity. Other forms of energy, or other places where you detect energy somehow with your human senses.
Thermal energy.
Very good.
Kinetic and static.
Excellent. Instead of static energy, I'm going to write down potential. Very good list. Any others on the tip of anyone's tongue before I start elaborating? All right, so most of these do refer to different forms of energy, and you do not detect any of them directly, only indirectly. I'm going to work up from the bottom to the top. Potential energy, you can't really see at all, because that's just energy something has and isn't using currently. It's stored for use later. You only really know how much it has until, you don't know how much it has until it starts transferring it into another form to do something with it, right? Now we have ways to estimate it. We're going to talk about gravitational potential energy this semester, and you can gauge how much gravitational energy something has by observing how high it is above the ground. But even that's still relative because it depends on your frame of reference. So, again, you don't perceive the potential directly, you just perceive what something does with the potential once that potential is unleashed. And it does depend on your frame of reference. There's lots of different forms of potential as well. I'd say most famously gravitational potential, but also chemical potential, which is pretty important to human biology. Kinetic energy is the energy of motion, which again you can only detect when something is actively moving. And that's still not a good ballpark for detecting kinetic energy, because secretly everything is moving. Because the planet you're sitting on is a rocket ship hurtling through space at Mach 9. We are moving right now, just not from within our own frame of reference. So using our Earth-based tools, if I tried to measure your current velocity and kinetic energy, I'd get 0. But from galactic perspective, you've got a ton of kinetic energy and we just can't detect it because we can't see galactic motion between ourselves. So again, flawed based on frame of reference, and you can only see it indirectly if something is moving from your frame of reference. Thermal energy, you only detect it through the random motion of particles, and even then, the human nervous system complicates measuring thermal energy even more than that, because you do not detect thermal energy itself, you only detect if thermal energy is entering your body or leaving it. Can anyone tell me how many joules of thermal energy they currently possess in their body without using external tools or formulas? No. If you can, I'd be very impressed. Please write that up and submit it to Nobel. But I assume that you can't. And even more than that, no, what was my point? That's a sign I need more water. Your perception of temperature, and temperature is again not even a good metric for thermal energy, not total thermal energy level anyway. Your body doesn't have a thermostat. You don't sense temperature, you just sense heat flow. If you're currently in equilibrium, like I feel pretty equilibrium in this room in terms of temperature, I don't feel hot or cold, which implies that the air is about the same temperature as the outer layer of my skin. I don't detect any heat flow because it's not flowing, it's just equalized. And I only feel temperature when it's at a different temperature and the heat is flowing. So that is flawed. I possess thermal energy, but I don't detect it right now. I only detect when it's moving. And even then, you don't really detect like how much energy, you just detect if there's a lot of it entering you through the scrambling of your nerve endings, or when there's a lot of it leaving you, which is also just scrambling your nerve endings. So again, also only sensed indirectly. Electricity is weird because the electricity itself is not energy. The electricity is matter moving because it has energy. It's weird to think about, but lightning is matter, which means it has mass, which means you could weigh a lightning bolt if you could hold it still long enough. It's made of electrons and air. The only reason you can see lightning is because when electricity passes through air, it leaves energy behind in the air, and flash turns it into plasma, and plasma glows, which is how light bulbs work. Well, at least how these light bulbs work. Rather than a filament, they just run current through gas, and the gas lights up by turning into plasma. So it's not that different from neon signs. So, electricity isn't energy. Electricity is moving matter, weirdly, just specifically electrons. And it then just leaves energy behind in things. And then lastly, light, which is also not technically a form of energy, but it's about as close as we can get to sensing energy itself. Light and all forms of radiation, so radio up through gamma, is energy. Well, no, it's not. Again, it's not energy. It's an electric field traveling alongside a magnetic field. So that's not technically energy because fields aren't energy. but it's the closest thing you can get because it's not solid and you can only detect it when it strikes something. So this is about as close as we have to measurable pure energy. The rest of it is, again, indirect. I can monologue about the weirdness of this all day, so to keep from doing that, I'm going to skip to the best definition of energy that physics can provide at this level. Energy is something that matter can possess that allows that matter to do things, such as move, or melt, or illuminate. Now, that list over there is good because it points out there are lots of different forms of energy. And the act of doing work not only uses it and gives it to other things, but actively transforms it between states. So that's why the transformation part is there. Every action you take, just based on how the human body works, does all three of these at once, because most of your motions involve muscles, and your muscles need stored chemical energy in the form of ATP to be able to do anything, right? So every time you move, that is not just, using the energy, it transforms it from chemical potential to the kinetic state, and then possibly gives that kinetic energy to another object. So most of the time, all three of these things happen simultaneously. And this formula can be used to describe all of them. We're going to focus a lot on the transformation part next week. Right now, we're going to focus mostly on the use part. But this formula does involve the transforming of energy between states. Questions from that monologue? All right. So with all that said, we did just learn a new formula, so let's get some practice in for it, because it has a few quirks that one needs to be familiar with. We've been pushing boxes around in our examples all week, and that's set to continue. We're going to push a box with 50 newtons of force, and we are going to slide it forwards in the same direction by 10 meters. How much work do you accomplish during this task? Yep, it's not a trick, I promise. 50 newtons applied, times a displacement of 10. We accomplished 500 joules of work in this action. That means, at minimum, we are giving the box 500 joules of our own energy to allow it to move. So from start to finish, your body has at least 500 joules of chemical potential energy stored in it. You then transform that energy into the kinetic state, transfer it to the box, and the box uses it to move. All in that one action.
It weighs it weighs 100 newtons, or
Yes.
its mass is 100 newtons?
Weight. Because newtons is force and gravity is force. If it was mass, it would be kilograms.
Oh, okay.
I haven't mentioned the weight out loud yet because I'm going to get to it shortly. I wanted to make a few other points first. If you translate this into calories, it would tell you how much energy at minimum you burned in order to do this task. That would be like 125 heat calories and 0.1 food calories. And that represents, again, the energy the box gains from this process. Because this is the box's perspective. The box does this much motion while this much force is exerted on it. So the box gains this much energy. From your own perspective, due to pesky things like friction, you're actually going to use more energy than this, but this is just what the box gets from its own perspective. So, next thing I will point out, this is not the only force that acts on this box if it's sliding across the ground on planet Earth, correct?
Yes.
There's loads of other forces here. The slide highlights one of them in particular. The box's weight, 100 newtons down. So that force is present as this box displaces. So, my next question is, how much work does gravity do on this box in this scenario?
-100 newtons.
That is a good thought, and I want you to hold on to the idea that negative work is a thing. We're going to come back to it later.
Wait, it doesn't travel any in the y-axis.
Correct.
So,
I haven't acknowledged it out loud yet, but this formula has this little parallel symbol here that I hope you wrote down. That symbol is also on your formula sheet as well, where this formula is the first thing in the energy stuff bracket, and the parallel bars are right there. That means for this formula to work right, the force and the displacement must be parallel. They must be in the same axis. Work may not be a vector, but the two things you use to calculate it are, and they have to be in the same axis. The reason work isn't a vector is because in 1600 we talk about different ways vectors multiply into each other, and one of those ways ends up canceling out their directions. So you can multiply two vectors and get a scalar, and that's what's happening here. So work's not a vector. You don't have to worry about like joules north, because that's not a thing. But in this weird case, two vectors multiply together to create this scalar. And since they're both vectors, direction matters, and they need to be in the same axis for this formula to work right. And that means there's two ways to interpret how this formula would work here. I'm going to write out both of them. So WG for work, gravity, just to be specific. Work equals force parallel times displacement. So let's plug in the amount of force that gravity exerts. And now we need to multiply it by the displacement of the box that is parallel to that force. Gravity points down, so what is the box's vertical displacement?
0.
0. The y component of that 10 meters is 0. So gravity accomplishes 0 joules worth of task in this scenario. There's another way to get that 0 answer, and that would be starting from the displacement's perspective. So we're going to think about it in the x-axis instead of the y. The box moves 10 meters within the x-axis. How much force does gravity exert that is parallel to that displacement? 0, again, the x component of this vector is 0. So that is another way to prove that gravity is not accomplishing anything in this scenario. We, the collective human in this case, are the ones pushing the box. We are pushing it forwards and it is displacing forwards. We are the ones accomplishing our task, accomplishing work. Gravity is just being a nuisance and not getting anything done.
Does gravity have energy?
Gravity, okay, I'm going to get to that point. I have to get through a few steps. Gravity can do work, because any force can do work. Gravity may not be doing work here, but it can do work if you are displacing vertically, which looks like this. So gravity mostly does work when things fall. So it can do work, and that means it can transform energy, but gravity, whether or not gravity has energy is kind of a weird question. It is able of transforming energy, because when I lift something, I'm giving it a form of energy called gravitational potential, and then when I drop it, gravity does work to transform that potential into kinetic. But technically, I gave it the original energy and gravity didn't. So the best thing to say is things other than gravity give energy to things, and then gravity transforms that energy. So gravity doesn't make energy, it just transforms it. And so when we say use a water mill to power something, that's supposed to be a water turbine, sorry. What's happening here is gravity is doing work on the water that falls. Gravity does work on the water, the energy becomes kinetic, and then the water itself transfers that energy into the wheel. So the energy doesn't come from gravity, gravity is just changing it into a form we can use. As a weird way to answer the question. Does that answer the question? Okay. Yeah, it's odd. Field forces like gravity, and also to the same degree magnetism, they're odd in that the force just seems to come out of nowhere. They don't technically add energy to things, they just unleash energy it already has, which is really weird in the case of magnets. So it's an odd, I could teach an entire class about that, if I'm being honest. Like, the source of gravity and magnetism and how they affect our lives is its own degree of science, its own branch of science entirely. So it's an interesting can of worms you opened. My best answer is no, it just transforms energy. That is my best answer for right now. Does that satisfy the question?
Yes.
Okay. Anything else on your minds presently? Okay. So the parallel rule. Force and displacement must be parallel to accomplish successful work. It is possible for non-parallel forces to act on an object while it moves. For example, let's say that I am an extra in a Marvel movie. I'm trying to push the box this way. Hulk enters the scene and decides, no, it's going that way. So the Hulk pushes it to the right, displaces to the right. The Hulk's gonna do work. I, assuming the box doesn't actually budge at all in the vertical axis, will accomplish nothing. I will do no work, I will get no work done, and I will not give the box any energy that it can use. The weird problem with this formula is I do still use up my own internal energy when I try this. It's just pointless.
It's not being exerted on the box.
Say it again?
The box is not accepting that energy?
The box isn't going to benefit from it. It's kind of static friction would hold the box in place, and that means that
Gravity.
friction is kind of taking all the energy away, so the box isn't benefiting from it. Instead, I'm just kind of pointlessly tiring myself out. You can use up your own energy and not do work. Work is the successful transfer of energy to accomplish something, but you can still burn up energy without doing positive, successful work. Like, to kind of replicate this, I can push on the wall and tire myself out doing it, and the wall's not gonna budge. The wall's not gonna actually get that energy, and it's not gonna do anything, but I'm gonna tire myself out. So the problem with this formula is, again, it only really represents how much energy the object receives, not how much energy we have to exert to get the task done. So So the purpose of this formula is from the perspective of the object being worked upon, and it tells you how much energy it receives as a result. Questions regarding that statement? Okay. Now, any force can do work, literally any of them. The object just has to move within the same axis as the force. And because of that fact, we can enter some weird scenarios where this formula will give us a negative number, which we call non-conserved work. Ideally, you want your work to be conserved. Conserved work means that when you give something energy through conserved work, that object has the energy in a mechanical state and it is still using it to do something. Conserved work in this case would look like giving the box energy, kinetic energy, to allow it to move. It would keep that kinetic energy and it would keep moving because of it. However, on Earth, do things tend to keep moving after we start them moving if we leave them alone? If we give something energy to move and then we just leave it be, does it keep moving indefinitely, realistically? No. I hit the scissors there. Why does it stop?
Gravity and friction.
Friction, yes. Gravity, indirectly, because gravity contributes to normal force, which contributes to friction, but friction, yes. What happens here is, I do conserved work, meaning that I am giving the eraser, energy. It has that energy in a mechanical state that we can measure and that we could use, because if I say, push this thing forwards into like the turbine of a generator, the energy would transfer into the generator and then we can use it for stuff. The problem is that friction does non-conserved work. And as soon as I move that box forward, friction automatically springs into existence, right? As soon as it starts moving, or even threatening to move, friction is going to rear its ugly head and try to slow this process down. And friction is a force. And any force can do work as long as the force is parallel to the displacement. In this scenario, what direction is friction going to point in? Leftward, very good. If the box moves to the right, friction would point to the left. And leftward might be negative, but it's still parallel to the displacement. It's still in the same x-axis. And that means we can use this formula and get a number for how much work friction does. So let's put some numbers to that to build the context. Let's just put a number on friction and say that it's going to be 30 newtons backwards. It's parallel, so it'll work, but we still have to note its direction relative to the displacement. These are still vectors. So, whoops. Work friction is going to be negative 30 times 10, because the 10 is positive and the 30 points opposite it. They're different types of vectors, but we still have to note their direction. And because friction points opposite the motion, it's going to give us a negative answer for the amount of work that friction is doing. That means non-conserved work, and that means friction is taking mechanical energy out of the system and rendering it useless. I mentioned that work is the use, transfer, and transformation of energy. Friction's entire purpose in the universe is to exert force on moving objects. And since that force always opposes the motion, friction is always doing negative work on those objects to transfer energy out of those objects and transform it into a useless state. Because once friction starts acting to slow something down, not only does the object not have the energy and therefore stops, we can't use the energy that friction stole. What form does friction tend to turn energy into, do you think?
Non-conserved.
It is non-conserved, and the form of non-conserved work becomes obvious when you start doing this. Thermal. That's why friction always warms things up. Tire tracks on the road, if you slam on the brakes and physically go feel the tire marks you leave on the ground, they're hot because the friction from the road on your car took all the kinetic energy your car had and just turned it into heat in the road. And once it's heat, you can't really get it back. Like if the car was still moving forwards, we could harness that somehow. Most cars have an alternator that turns kinetic energy into electrical energy to power your battery. But once it's in the road, you can't benefit from it. It's just making the earth hot. Which is kind of a problem for multiple reasons right now. Friction not only gets rid of useful mechanical energy, it turns it into useless thermal energy. Like, the only good thing friction does is warm you up, really. And even then, once you're warm, friction can make you too warm. Friction can take too much energy away. The main problem with friction is it is constantly leaching away all of the mechanical energy of the universe and slowly turning all of it into thermal energy, which is contributing to something you may have heard scientists and science authors talk about, the heat death of the universe. Question?
So for that box problem, would we say the amount of work done on the x-axis is 500, or would we only say 200 joules?
The box, overall the box would receive 200 joules. And that would determine how much energy it has to determine its speed. If friction didn't exist and we could give the box all 500 of these joules, it'd be moving pretty quick. But if friction does exist and it's working against us, the box only really receives 200. As a result, it's much slower. So yes, the net amount of work the box actually benefits from would be 200 joules. And that would be the total amount of energy the box gains, and we'll focus on this more next week. If it's only gaining 200 joules of kinetic energy, it's going to be moving a lot slower than if it gained 500. So friction slows things down, first of all, and also takes away useful kinetic energy and turns it uselessly into heat. Did I answer the question? Okay. Yeah, the box's perspective, it only gains 200, meaning everything is slower and worse than if friction didn't exist here. Since every motion you will ever take involves matter moving through or across other matter, there will always be a force of friction, and that means there will always be some amount of negative work friction is doing to mitigate the entire process. And this is why we overheat when we exert ourselves, because there is friction inside your muscles. I'm not a biologist, but I do know that for your muscles to work right, your muscle fibers have to slide over and across each other, correct? And that's matter sliding over matter, which spells friction. So there is friction in your muscles. No matter how much energy you currently have, every time you move, the friction inside of your own body takes some of that work you just did and pointlessly turns it into heat inside your own body. Every single thing you do will eventually lead to you overheating if you don't stop to cool off. Because every single action just generates more heat. And that's besides the fact that as warm-blooded animals, we turn some energy into heat to keep ourselves alive anyway. So that's just even more heat than we need, really, if you're, doing a lot of activity. This is why organisms overheat. It's also why your machines overheat, because there's friction in the parts of your car, and that's why the engine warms up and will melt if the coolant system isn't working right. And it's even why your electronics overheat, because there's friction involved in electricity. It's the motion of electrons, that's technically still matter. It's not traditional friction, but it still leaves thermal energy behind, pointlessly warming up your computer, again, until it melts unless you have a good cooling system. Or, turn it off. Friction is a big old pain, and it will continue to be a big old pain in most examples we look at moving forward. Main thing to focus on right now is I'm going to use this formula to talk about all three of these actions, using, transferring, and transforming energy. Next week, we're going to look at different types of energy, how friction continues to mess things up, and we'll also talk about the physics definition of power before we move into test review territory. Questions right now? All right, it's Friday. Get out of here and have a nice weekend. Let me know if you need anything.